All right, so what we're getting on to here is section 3.2. We're looking at polynomials and their graphs. If we look at some examples, the first one I can write down is actually what we were just doing, which is the quadratic functions. They are polynomials. Ax squared plus bx plus c, something of that form would be a polynomial. Another example might be something like g of x equals x cubed plus 3x squared minus x plus 1. Something like that would be a polynomial. Another one might be like h of x equals 4x to the 10th minus x to the 3rd minus x, or something like that. Just anything like that where we have that. Some of the main characteristics of the polynomials, this main thing you're going to look for is all of your exponents are whole numbers that are greater than or equal to 0. And what I mean by they can be equal to 0, that's for something like this here. This 1 is really 1 times x to the 0, because remember, anything to the 0 power is just 1. So if you have a constant in there, it's just times x to the 0 power. Same thing over here. C would be c times x to the 0 power for that one. So those would even count. The next thing you're interested in is the leading coefficient. This is essentially the number, right, in front of the highest power of your variables, which is usually, in our case, is usually x. But if you go into some other classes like physics or something, you might get a polynomial that has t in as the variable instead of x or something like that. So it's the highest, it's the number out in front of the highest power of your variables. So for example, in the f of x equals x squared, this one, ax squared plus bx plus c, whatever a is, would be your leading coefficient, because that x squared, it has the largest exponent, and therefore that is what is called your leading term. This is your leading term, and then that leading exponent, or that leading coefficient that's out in front of that term, would be your leading coefficient. Over here on this one, x cubed is our leading term. It has the highest exponent, and then there's a 1 out in front of it. So the leading coefficient would be 1. So things like that. The degree of the polynomial is just the highest power. It's the highest power of the variable, which is typically x, the highest x exponent. So you find that leading term where you have that highest number, and then whatever that power happens to be, that's what your degree is. So in this first one here, this one would be a power of 2, a degree of 2, because we have that power of 2 there. This one would be a degree of 3, because we have that 3 exponent right there. It's our biggest one. This one would be degree of 10, because we have that 10 right there. That would be our highest degree. Now, don't pay too much attention to the order. I could write this same one as negative x cubed plus 4x to the 10th minus x. And even if I wrote it this way, it is still degree 10, because that's the largest number we're looking at. Now, typically they are written from greatest exponent to least, but they don't have to be. So just be careful of that. All right, so let's take a look at an example here. It says identify which of the following functions are polynomial functions. If it turns out that it is a polynomial function, then identify the degree and the leading coefficient of the polynomial. So I look at this first one, and I don't see anything. I don't see any sines or cosines or logs or anything like that. It's all just x's to different powers. So that's good. And then I look at each power, and every power is a whole number. They're all whole numbers. There's no negatives. They're all positive whole numbers. This, again, remember, is x to the 0. This one was to the first. So they're all positive whole numbers. Therefore, this is a polynomial. So this is a polynomial. And since it's a polynomial, I need to identify the degree. So the degree, which I'm just going to write as a d from now on, all right, the degree is going to be 5, because when I look at this, 5 is my largest exponent, and so this is degree 5, the largest exponent on my variable x. And then my leading coefficient, right, which I'm just going to write LC from now on, is going to be this 3. It's right in front of that leading term that had that x to the 5th in it. That's our highest power. So I just grabbed that number right out in front. That's the coefficient. And so it has a leading coefficient of 3. All right, so what I'm going to do now is pause this and check for any questions, and also give you a chance to go through and try these last ones to decide if it's a polynomial. And if it happens to be a polynomial, then go through and actually tell the degree and the leading coefficient. All right, there's all the answers to that one. So if you need to, pause and take a look through them. Moving on, here we have graphs of polynomials. Whenever we have polynomial functions of degree 2 or higher, we have graphs that are smooth and continuous. Technically, any polynomial, even below degree 2, is always continuous, that idea of smoothness, because any degree 1 polynomial is going to be like a y equals ax plus b. That's just a straight line in slope intercept form, like mx plus b. Maybe I could have written that, mx plus b. That gives you a straight line. And then, of course, the degree 0 is when it's just a constant, like y equals 5. Those are both just straight lines. So they are continuous, but they're not curvy. All right, anything of degree 2 or higher is going to be a curvy kind of smooth and continuous. And what I mean by smooth is there's going to be no right angles. There's going to be no sharp corners. It's continuous. There's going to be no jumps or holes or gaps or breaks or anything in it. So they'll look something like what's in those pictures. Down here, you see examples of graphs that are not polynomials. You can see here, we have a break. We have a jump where it jumps down like that, and we have a hole there. That's not acceptable. Over here, you can see we have sharp corners. That's not going to happen with a polynomial. That means it's not smooth, even though that one's continuous. So first one isn't continuous, even though it's smooth. The second one is continuous, but it's not smooth. And then this last one is not continuous. It has a big jump in it, where we never actually get to this value of 0. In fact, this is the graph of f of x equals 1 over x. And so that is definitely not a polynomial, because that's x to the -1 and is not a polynomial. So when you look at graphs, you can identify polynomials by nice, smooth, continuous graphs where your pencil never leaves the paper as you're drawing it, and there's no sharp corners. That's what they're going to look like. If you have to lift your pencil to keep drawing it or make a sharp corner, then it's not going to be a polynomial. Okay, so what we're looking at here is end behavior of polynomial functions. And what we're going to look at is the leading coefficient test. And the reason we're doing this is because the majority of the function's properties by a long shot are going to come from that leading term. All right, when you look at that leading term, like if we have an x cubed plus x to the squared plus x or something like that, this x to the cube here is going to be extremely dominant at big numbers. So for example, if I have like, if I'm looking at 1, if I'm looking at x equals 1, then it's just, they're all 3 equal to 1, right? It's 1 plus 1, 1 plus 1 plus 1. And they're all pretty much the same. Even if I go to a number like 2, where x equals 2, then x cubed is 8, and x squared is 4, and 2, and 8, 4, and 2. They don't have that big of a difference. But if I look at something like x equals 1,000, well, then x to the third is going to be a 1 with 9 zeros. All right? It's 1,000 times 1,000 times 1,000. And so that's a billion. And x squared is 1,000,000. And the difference between 1,000,000 and 1,000,000,000 is a lot bigger than the difference between 2 and 8. So even if the x squared term, like say this x squared term was negative, like it was minus x squared, this would be negative 1,000,000. Well, negative 1,000,000 is not that big of a deal compared to 1,000,000,000. Compared to 1,000,000,000, 1,000,000 is not much, and it's not going to affect it. And so if we looked at this, we would be much more interested in what was happening here with this billion as to telling us whether or not the graph was increasing or decreasing as we went towards a certain value, as we go towards the really big values. And if you think about going to like 10 to the fourth or something like that, something even bigger, then the differences just get larger and larger and larger. This x to the third gets bigger much, much faster than anything else because it's the leading coefficient. If we stuck an x to the fourth on here, then it suddenly would dominate as we got to really big numbers or really negative numbers, because it would be by far the biggest. It would grow the fastest. So that's what you're looking for. You're looking for whatever that leading term is, and it's going to tell you the behavior of the graph. Maybe I should leave that up there. So anyway, what we can do is look at this. First off, we're going to think about x squareds. Whenever we have our leading term having an even number, so our degree of our polynomial is even, we're going to think about the x squared graph. And the x squared graph looks like that. And what you can see in the x squared graph is that as we go in the positive direction or the negative direction, this graph is going up and increasing on both sides. So if you go to the right or you go to the left, it is increasing in both directions. So if our degree is even and our leading coefficient is positive, this is the kind of behavior you're going to have. It's going to go up to the left and up to the right. So you might even see it sometimes just drawn with arrows like that, up, left, up, right. Here, sometimes they also say it rises left, rises to the right. Another way it might be said is something like as x goes to negative infinity, y goes to positive infinity, or as x goes to positive infinity, y will go to positive infinity as well. So something like that. So as x goes to negative infinity, that's going to the left. As x goes to positive infinity, that's going to the right. And so you might see it any one of these three ways. I'll probably write it that way as a shorthand, but you might see the answer written that way, or especially on the test, it's going to probably be written something more like that. So you need to understand all three ways that that is written for their little shorthands. The next one is if the degree is even and the leading coefficient is negative. If the leading coefficient is negative, you're basically think of a negative x squared graph. This has a negative out in front of it, and so it's a vertical flip, right? It's a flip over the x-axis for our graph, and therefore it's going down to the left and down to the right. So I would draw that kind of like this, arrows pointing down to the left and down to the right. We could also say this as falls left and falls right. Both of those would be correct ways to put it. And then maybe the last time I'll write this out, but we could say something like as x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y will go to negative infinity, like that. And so any one of those three kind of ways will be it. And again, I'll probably just start putting that as my shorthand for it. So essentially, if you have an even degree for your polynomial, either both sides are going to go up or both sides are going to go down. And again, we're not talking about what happens near the origin. If we get in there, there may be all kinds of wacky stuff going on. We're only interested in what happens when we go to the extremes. As we go really far to the right or really far to the left, what's going to ultimately end up happening. All right, so even polynomials, even degree polynomials are either both up or both down. Now, if the degree is odd, think x cubed has an odd degree, then one side is going to go down and the other side is going to go up. If the leading coefficient is positive, then it's going to go down to the left and up to the right, just like the x cubed graph would do. All right, if it's leading and it's positive. So this is, you know, it's falls left, rises right. So something like that. And then if the degree is odd and the leading coefficient is negative, that is like thinking of negative x squared. And so, or negative x cubed, sorry. Think of negative x cubed. Negative x cubed is the x cubed one, but flipped vertically. So instead it ends up rising to the left and falling to the right. So it rises right, falls left. Okay, that's what that one is going to look like. So anytime you have an odd exponent, it's going to have the same end behavior as x cubed. Every time you have an even exponent or an even degree leading coefficient, we're going to have it follow along the same type of thing as x squared does. All right, so let me pause for a moment and see if there's any questions here. All right, so just for the recording here, I went ahead and wrote the as x goes to negative infinity, y goes to negative infinity parts for those last two. Plus, I also had it pointed out to me that over here, highlighted in green, that I had flip-flopped those when I wrote it down originally. So make that correction. It should rise left and fall to the right like that. Okay, so let's go on to the next page here. He says, let's just do some examples of this. So we're going to use the leading coefficient test to determine the end behavior of the graph given the function. So if we look at this first one, we see that our leading term here is this x squared. We see that it has a degree of 2 that is positive, right? It's positive. And then after that, we look at the leading coefficient. The leading coefficient is 1. All right. Oops, that shouldn't have been a positive there. What am I doing? So I saw that get messaged to me on the screen and I wrote it down. It's a degree 2. It's even. And the leading coefficient is 1. It's positive. There we go. So it's even and it's positive, which means if we come back over here, this is our even positive situation right there. And so it rises to the right and rises to the left. It's like looking at an x squared graph. So this is going to rise to the left, rise to the right, and that's what I'm going to just write the answer as there. I'm not going to write the other two ways out. You should be able to write those down. So that's essentially what you're going to do here. Determine the degree, if it's even or odd, and then determine that leading coefficient to decide which of those 4 outcomes it could possibly be. So I'm going to go ahead and pause this and let y'all start working on these.